Now let's begin section 6.3, volumes by cylindrical shells. As the name suggests, this is a continuation of the previous section. We are still on volumes, and we are still on the solid of evolution, and consequently, that calls for a review. So let's move on to my Mathematica notebook here. Let's initialize it before anything, and here are the general volume formulae. When the cross-sectional area is given as a function of x, then we have to use the first formula. When it is given as a function of y, then of course we have to use the second formula. The typical cases include the solid of revolutions, and here they are. Solid of revolution is given by, well, as the name suggests, the revolution. So we have to have circular cross-section. Consequently, the cross-sectional area is pi r squared, and the radius r can be either a function of x or it can be a function of y, depending upon the position of this axis of rotation, of course. This is a quick review, so we'll just go over to one example as quickly as possible. Here, let's begin with y equals e to the negative x cubed. When x is greater than or equal to 0 and less than infinity above the x-axis, as we see here in this gray region, and rotate this region with respect to the x-axis, and we're going to get this kind of picture. Please note that the same 2D picture we saw before is generating this 3D figure by this rotation with respect to the x-axis. If we change the viewpoint, then you can see a rotation a little bit more clearly, kind of like this. The x-axis this time is coming directly to you. In the next visualization here, we can actually see how the volume formula is being driven here. As x changes from 0 to infinity, you can see the cross-sectional area of the coin changes kind of like this, and the radius is given by the y-coordinate value. So pi r squared is nothing more than pi y squared, and into the computation, this is what we're gonna get: pi x e to the negative x cubed. That's your y value, isn't it? That thing squared. So we have this kind of volume, and we're gonna need some substitution and some limit computation to get it done. The detail is left to the student. Next, let's review washer method. In the previous example, if we have just one curve and rotate it around a certain horizontal line or vertical line, we don't have any hole. In some cases, however, we can have some hole inside, so we have to subtract away the volume of the hollow region. Consequently, we have this subtraction. R squared, capital R squared, is given by outer radius, and small r squared is given by inner radius. Either this one or that one have to be used. And the example we are going to go through will employ the first one. Here, y equals to x squared and y squared equals to x. And those are red parabola and blue parabola in the first quadrant. The area, the green region captured by these two curves, is being rotated with respect to the x-axis. And if I change my x-coordinate value from 0 to 1, you can see the radii changes. The blue circle and the red circle in the right hand side. Please remember the right hand side picture. And then here is the visualization of the revolution. So if you take the same region and rotate it with respect to the x-axis, and we generate this kind of 3D solid, how do we find out the volume of that solid? Well, here's a visualization of the washer method. So if I change the x-coordinate value from 0 to 2, you can see that the cross-sectional area changes the way we have over here. We have the area of the washer, and the next picture will give you even better review. So left hand side, we saw the same picture we saw before, the washer, the cross section. The right hand side is 2D figure of that cross section. So how do you find out the area of this cross section? And the blue circles inside of the blue circle minus the inside of the red circle. That's how we get pi capital R squared and pi lowercase r squared in the formula we saw before. Okay, that was a quick review, and I still spent more than 5 minutes. Okay, let's move on to the shell method. In some cases, the washer method simply do not apply. And here's one such example here. Let's begin with y equal to 2x squared minus x cubed between x equal to 0 and x equal to 2 and above the x-axis, and that's visualized as green region in this picture below this blue curve. Take this region and rotate it with respect to the y-axis, and we are going to get this kind of 3D solid. Please note that the same 2D region we saw before is generating this 3D solid by rotation with respect to the y-axis. Somehow this figure reminds me of a bundt cake. I don't have a hole inside, but still kind of looks like a bundt cake. You don't have to agree with me. Anyway, let's try to apply a washer method to calculate its volume. Or you can use two coin methods, whatever you want to do. In any case, here is the difficulty. So we are rotating with respect to y-axis. So y is running from 0 to about 1.2, but you have to find out precisely how do we do that. It's difficult but not impossible. What you need to do is to take the derivative, set it equal to 0, blah blah blah, and then you can find out the absolute maximum. Difficult but not impossible. But what are the outer radius and the inner radius? This one and that one. The distance from the y-coordinate axis and the right-hand side edge of this curve, or the x-coordinate value of, well, these points over here in the right-hand side edge, will be the outer radius. As a matter of fact, I should have highlighted this part over here. And that's very difficult to find out. How about the inner radius? That's gonna be the distance of the distance between the y-axis and then the left-hand side edge of this region, the left-hand side curve. Again, those are the x-coordinate values. How do you find out x-coordinate values when you know y-coordinate value? You have to find out an inverse function, and that was not too bad when you had a quadratic function. You can take complete square and then take plus or minus square root. Great. But what if you have a cubic function? That's very different story. As a matter of fact, our textbook author is asking you exactly the same question here. In figure 1, we have the same picture, y equal to 2x squared minus x cubed. And what is left-hand side xl? What is right-hand side xr? What are the x-coordinate values? That's not easy. I don't think it is. Oh, it is possible. This is cubic function, so it is possible. Difficult, but not impossible. But if it is quintic or higher, then flat out impossible, at least algebraically. So what we do, we need an alternative method, and one such method is a method of cylindrical shell. Okay, before explaining the method of cylindrical shell in rigorous detail, let me give you one warning. This derivation here, this computation, is not entirely right. I have an issue about that, so I'm going to postpone this part and talk about it next segment of the video, which I think a lot of people will simply skip. And let's go over to visualization and an example problem in this set. Let's postpone that example and then let's go over to figure 3. Let's consider the first picture. This is 2D figure, and a 2D figure given by y equals to f of x between x equals a and x equals b above the x-axis, and rotated with respect to y-axis. Consequently, we get some picture like this with a hole. Now, how do we find out the volume, or how do we represent the volume of this solid as a definite integral? That's the question here. Let's move on to the next page to see the answer here. So we have the same 2D picture in the first picture, figure 4, and we take a rectangle, a shaded blue rectangle, and rotate it with respect to y-axis. What do we have? We have a cylindrical shell, as you see here in kind of yellowish gold figure. And then what do we do next? We take not just one, but 1, 2, 3, 4, 5 rectangles from A to B and rotate all 5 of them with respect to the y-axis. What do you get? You get 5 cylindrical shells which approximate the original 3D figure. The third one is a kind of routine thing. Whenever Riemann sum shows up, we take finer subdivision and rotate them around. We have a bunch of cylindrical shells, and some of them will, I mean by SUM, the sum of all these volumes of these cylindrical shells will approximate the original volume very, very well. The thickness of each cylindrical shell is given by the width of each rectangle in this original blue 2D figure, and obtained by delta x, and that height will be my function value f of x. And in the end, we end up with this formula here, 2 pi x f of x dx, where integral is going from a to b. Now, how do we derive this formula? That's an important question, but I'm going to answer that question in the next segment of the video. And let's move on to an example problem. Let's pause this a little bit. Okay, let's get back to the same example in my Mathematica notebook here. And same 2D picture. And same 3D figure. And here is a visualization of the cylindrical shell, as a matter of fact. So if I change my x-coordinate value from 0 to 2, you can see a cylindrical shell forming here in the left-hand side 3D picture. This line segment, it looks like a line segment, but as a matter of fact, you have to understand it as very, very thin rectangle with delta x is so small that it looks this thin, and rotate it around the x-axis, and we have a cylindrical shell with infinitesimal thickness. And then summing them up, we're going to get a Riemann sum, and we have a computational formula like this. As a matter of fact, let me insert one more. Oops, I shouldn't have done that. So from A to B, 2 pi x f of x dx was the formula given in our textbook, wasn't it? And then x is actual radius, as a matter of fact, radius of this cylindrical shell. So the distance between the x-axis and this line segment over here, correction, distance between this line segment and the y-axis, and rotate it around as we see in the left-hand side 3D picture, then that's a radius. So that's that, and the height is f of x. And in this particular case, computation was very simple. 2 pi x times, well, f of x. And what do? You just multiply them out, apply the power rule, apply the fundamental theorem of calculus, do the computation, and you have an answer. So the computation was very, very simple. Once you begin an integral, it's not too bad. But getting into this formula is a big deal. And in this particular example, the simplest version of this formula, a to b 2 pi of x, 2 pi x f of x dx was working well. But in some other situation, you have to work out the radius. So this x will have to be replaced by r of x, the radius. And f of x will be a certain height that we have to work out. And we're going to discuss those in the next segment of the video.